So my name's Tom Catalino. I'm with Critical Link, which is a third party of Texas Instruments. We're part of their TI design network, and we're one of their platinum members. I believe there's only about 20 or so platinum members of the TI design network worldwide, and Critical Link is proud to be a part of that network. What we're going to be talking about today is a custom machine vision solution that we're demonstrating over here in our little pod. And the machine vision solution we're going to be talking about today is based on the OMAPL138 and the system on module from Critical Link called the Mighty DSP. This entire talk is based around a white paper that we did co-authored with Texas Instruments. That we'll give you the link at the end of the talk, so you can read the paper if you're interested. So, in this talk, we're going to be talking about a few different building blocks that we use to build this machine vision architecture. And the architecture is available in kit form for customers to purchase and develop their own custom machine vision application based on the OMAPL138. So the building blocks that we have to work with are the OMAPL138, and if you're not familiar with the OMAPL138 from TI, it's a 456 megahertz ARM9 married to a 456 megahertz 674X DSP, all in the same piece of silicon. The ARM is capable of running embedded Linux, and the DSP is there for you to do whatever signal processing, in this case image processing, that you would like to do in your product. The ARM, as I mentioned, is generally used and used in this vision development system for a user interface, whether that be communicating over the Ethernet to other parts of a system, or running the user interface in a local display. It can be any kind of communication with the outside world. Generally, that's a good place or a good function for the ARM to handle. In addition, it handles any of the higher level control that goes along with the interface to the outside world, communicating back down commands to the DSP in order to tell it what the user or the other parts of the system would like to command it to do. When we move down to the DSP initially is going to be acquiring the image data via the UPP interface. The UPP is a universal parallel port interface that runs into the OMAPL138. It's a very convenient parallel port interface that is 16 bits wide at 75 megahertz, and there's two of those channels. So you can run about 150 megabytes per second into the UPP interface, right into the DSP and the ARM. You can direct DMA that data right into SDRAM without processor intervention. So it's a real handy interface, and it's a real good interface for interfacing with programmable logic and other devices that have a parallel interface. Now, the DSP also has the ability to do, as we mentioned, image processing. And a couple of the libraries that are available to customers who want to produce their custom machine vision application would be ImageLib and VLib. Those are TI libraries. And then there's also open source libraries like the OpenCV library that can be ported and run on the DSP. TI has even spent some time porting the OpenCV library. So you'd have to contact TI and find out, availability on the open source OpenCV library for the DSP. In addition, we're going to be using the Xilinx Spartan-6 FPGA, and this is a cooperative effort. So in this system, we allow the FPGA to be doing some pre-processing on the data before it then passes the data across the UPP to the OMAPL138. The types of things that we can do with the FPGA are, first of all, we're interfacing directly to the sensor. In addition, we're doing image pre and post processing. We'll talk about that on the next slide a little bit. But one of the things that it does primarily is it calls down the data, right? So the OMAPL138 is, like we said, 456 megahertz ARM9, 456 megahertz DSP. So it's fairly low power. But that also means that it's not of the same processing capability of one of the higher-end DSPs that runs, say, a gigahertz or more and has multiple cores, which of course requires more power to do that. So in a lower power situation, the OMAPL138 is a good choice. But the addition of the Spartan-6 helps us cull down the data so that we don't overwhelm the OMAPL138 with too much work to do. A couple of different ways that we cull that data down is we do pixel culling. So you can have the FPGA searching through the image data as it flies through the FPGA and cutting down the pixels that get passed on to the OMAPL138. So when it finds a feature that it thinks the DSP or the OMAPL138 is going to be interested in, it clips that piece out and sends it on. Or you could implement a static or a dynamic region of interest using the FPGA itself. So just to give you a little bit of a high-level architecture about how this system works, we have the sensor attached to the FPGA, and we allow the FPGA to do inbound processing. So this might be the pixel culling that we talked about. It might be running an edge detection algorithm or some other type of algorithm that can process the data as it passes through. Once the Xilinx, the FPGA, has completed that, then it passes the data across the UPP over to the OMAPL138. There, it's passed into the DSP and then processed. And then on the back side, the data can then be routed back out through the other UPP channel, back to the FPGA where it can do some outbound processing if your application is so inclined, right? So you could put an overlay on the data, you could do some, highlight some specific information, and do so by using the FPGA, the programmable logic in the FPGA. And from there, the FPGA can send the data outbound to any of the outbound outputs that the data has to move on to from there. So breaking into, a level down into that architecture, we have the image sensor, and in the kit and in this system, we bring the data into a header. We're using an Aptina sensor, an MT9V032, but you could use any one of a number of different sensors in your application. In the FPGA, in this vision development kit that we have and in the white paper, we talk about how you can basically plumb in your own algorithms. So the algorithms, the culling algorithms that we talked about a little bit ago, can be plumbed into this architecture right here. But you can put almost any kind of FPGA algorithm into the code that you like, and you don't have to stick to this kind of structure within the VHDL. Then from there, the data is passed out to a FIFO, an outbound FIFO, and passed across the UPP interface to the DMA engine in the OMAPL138. And in our particular case, we pass it to a scatter-gather DMA engine, so it ends up in the memory, the SD-RAM, in a nice, convenient format for the application software and the DSP to work on. From there, now we're into the DSP, and the data becomes available for the DSP to operate on. This is where you plumb in any of your image processing that needs to process, say, the whole image all at once. This is where you might use your OpenCV library or your ImageLib or your VLib. You plumb into there any of your custom code to analyze and process the data for the custom machine vision type system that you're looking to build. In addition, here in the OMAPL138, there is an interface between the DSP and the ARM that is controlled by a library called DSP-Link from TI. And this allows that communication back and forth between the ARM and the DSP for the ARM to command the DSP to put it into different modes and do different types of applications. And in addition, the DSP can communicate through DSP-Link in order to share any kind of results of the analysis that it's done of the images. In our case over here at the demo, we have a frame buffer present in shared memory. So the ARM places the frame buffer into shared memory, and then the frame buffer is scanned out by the LCD device to push that out to the actual display. And that you see right here, that it goes into the Linux frame buffer, and then Linux just pushes that out frame by frame. So we've kind of covered this overall architecture. It's a fairly simple and straightforward architecture for doing again, a custom machine vision algorithm or custom machine vision product based on the OMAPL138. And places that you can go for additional information would be TI for the information on the processor itself, the couple of libraries, and then also the white paper on which this discussion is based. There's a little bit more detail in some parts of the white paper. In addition, you can go to Xilinx in order to get information about the Spartan-6 and the libraries that they have available for the FPGA. OpenCV is at opencv.org. And then finally, at Critical Link, you can get information about the actual Vision Development Kit if you'd like to take that and use it to build your own custom application. Or if you'd like to use just the Mighty DSP-L138 that marries the OMAP-L138 to the Spartan-6 FPGA system on module, that is this little guy right here. You can come to Critical Link or mightydsp.com/mightydsp-L138F. So my contact information if anybody has any follow-up questions later on, but are there any questions that I can answer right now? All right, thank you guys. Appreciate it very much.